In this lesson we're going to look at Newton's third law. Now before we explain this law, let's just state what it says. And it says this: for every action there is an equal and opposite reaction. So for example, if we look at this fellow here, he's pushing against this brick wall. We'll call his push the action, but at the same time the wall is pushing back against him, and we'll call this the reaction. So the reaction and the action are equal but opposite. The forces are balanced. Likewise, for example, we've got a cannonball sat on top of a tabletop. We've got a force pushing down on the table, so the action in this case is the weight, and at the same time that weight is balanced by the reaction, which is produced by the table pushing up on the ball. In the case of this weight hanging on a spring, again we've got the weight pulling downwards, and that's balanced by a reaction which is equal, and assuming that the weight is motionless like the ball on the tabletop or the wall, then that is balanced by an equal but opposite reaction pushing in the opposite direction. In this case the reaction has a name, it's called the tension. So sometimes the reaction in physics is given a name, for example tension, and in this case again we have the weight of the ping pong ball which is floating on the water acting downwards, and the reaction is called the upthrust. That's to say the particles in the water push against the wall to balance the weight pushing downwards. So we can look at Newton's third law in this way. We can say we've got object A, object B, object A, object B as in the table, object A as in the weight, object B as the spring, object A as the ping pong ball, object B as the water. And we can say that if object A exerts a force on object B, then object B will exert an equal but opposite force on object A. Now you might ask the question, if Newton's third law is true and every action is balanced by an equal but opposite reaction, how is it that anything is ever able to move at all? What I mean to say by this is that if the force exerted by an object on another is always balanced by an equal but opposite force, how do we ever get objects to accelerate? Because at first glance, the total sum of the forces, as in all of these cases for example, will be zero. It's actually a little bit tricky answering this question, and to do that let's have a look at the following illustrations. First of all, we've got somebody jumping off a boat on a lake. Okay, the boat weighs 200 kilograms and the person weighs 50 kilograms for example, and they jump off and they push with a force of say 100 newtons. Now Newton's third law says if this person pushes against the boat with a force of 100 newtons, then the boat will push back on the person with a force of 100 newtons. Okay, so we have the action and the reaction. What in fact happens is the forces are balanced here, but both objects move. So both objects will accelerate according to Newton's second law. You'll remember that F equals ma. That's to say there's 100 newtons pushing on the boat and an equal opposite force of 100 newtons pushing on the person that way. Of course the accelerations of each will be different because they have different masses. We can write the acceleration is equal to F divided by m, and in the case of this person the acceleration will be A equals 100 divided by 50, which would be 2 meters per second squared, whereas in the case of the boat the acceleration will be 100, the same force, divided by 200, which will be 0.5 meters per second squared. So as a result of this, the person jumping off will move faster than the boat, which will move away more slowly. So Newton's third law applies here. We've got an equal but opposite reaction. The force is the same, but they're both acting on objects of different mass. Let's have a look at this new situation. We've got a shopper pushing a trolley. So let's suppose that the trolley has a mass of 30 kilograms and the shopper has a mass of 70 kilograms. So their combined mass is 100 kilograms. Okay, and in order to push this trolley, where does the shopper have to push? Well, he's going to have to push against the earth, here where his foot's in contact with the ground. And let's suppose that he pushes with a force of 100 newtons. Now, as Newton's third law states, for every action there's an equal and opposite reaction. So as he pushes this way with a force of 100 newtons, the earth pushes back on him with an equal but opposite force of 100 newtons. So we have an equal and opposite force pushing back. So using Newton's second law, F equals ma, just as with the boat, we can calculate the acceleration of the shopper and his trolley. So we can say that the acceleration is equal to F divided by m, which is equal to 100 newtons divided by 100 kilograms, which is 1 meter per second squared. At the same time, the shopper is pushing against the earth with exactly the same force. So we can say the earth also accelerates. However, because the mass of the earth is absolutely enormous compared with the force with which the shopper is pushing, the acceleration of the earth is effectively zero. In other words, it doesn't move at all. Only the shopper and his trolley move.